Now, problem 7 as solved in the back of the book. Cleanly, I have nothing to add here. Problem 8 is given as a writing homework assignment, and I will not show you how to solve it for this reason. So the last problem I want to address is 11. In problem 11, we want to prove that f of n equals product over divisors d divides n g of d, then g of n is the product over divisors of n f of g taken to the power mu of n divided by d. This looks like Möbius inversion, and there is a hint to use logarithm. So we follow the hint and define capital F of n to be logarithm f of n, and capital G of n to be logarithm g of n. Now f and g, capital F and capital G, are also arithmetic functions, as f and g are. Their domain is the same, natural numbers n, while values of f are integers same about values of g. Of course, the values of capital F and capital G are far from being integers. These are logarithms of integers, probably transcendental numbers. We don't care, they are still arithmetic functions. Now, let us write this identity in terms of capital F and capital G. So we write what is given as in terms of these new functions. For that, we take logarithm of identity. Logarithm takes products into sums. So the given identity this one implies that logarithm f of n equals logarithm of product is sum of logarithms, sum over the divisors of n, logarithm g of d. In other words, capital F of n is equal to sum over divisors d divides n, capital G of d. By definition, which I have just recalled somewhere here, by this definition, we conclude that therefore capital F, capital G is a Möbius pair. Now our principal theorem in section 6-4, theorem 6.6, Möbius inversion formula, implies, well, I will write a theorem 6-6 implies that G of n can be written in terms of f of f and Möbius mu function as sum over divisors of n mu of d f capital F of n over d. We need a little bit different form, and this is about symmetry between d and n over d. This is a pair of divisors, a complementary pair of divisors of n. Their product is n. So this is the same thing, in fact, as sum over divisors of n, mu of n divided by d, f capital F of d. I hope this is clear, that d just runs over the whole set of positive divisors of n. When d runs over the whole set of positive divisors of n, so does n divided by d, the complementary divisor. In this formula, we just have mu of divisor, any divisor of n, times f of the complementary one. Same is written here, mu of any divisor of n, f of the complementary divisor. Now we can rewrite this formula. The identity G is equal to this sum in terms of small f and small g, which are originally given. So we can rewrite it as logarithm G of n is equal to sum over divisors of n, mu of n divided by d, logarithm f of d, which is the same thing. Mu times logarithm is going to be logarithm of f to this power, so let me rewrite it this way. And moreover, sum of logarithms is logarithm of sum. I will do both transformations, writing logarithm outside, and we have inside product over divisors of n f of d taken to the power mu of n divided by d. Now we can get rid of logarithms, returning back to the clean formula. Formally, we just take exponent of left hand side and right hand side. Take exponents of both sides with some, or if we want to be reckless, simply cross out these logarithms to get the desired identity. Well done. A very small remark here, we could write this powers mu safely, because you see mu is 0 or plus minus 1. If it was something else, we could be in trouble, but in small trouble, f is anyway a positive number, positive, no matter integer, it is just a positive number, so any power would be allowed, would be good here. So that's it. We got the identity. This one, g of n, is equal to the expression on the logarithm here. That's all. With that, I finish problem session about section 6 from the book. Thank you for listening.